This is a rehearsal test for the talk I'm going to be giving on Wednesday, November 12th at the New York Quantum Computing Meetup. This is Machine Learning on Quantum Computers, and my name is Larry Leibovich, and I'm an adjunct research scholar at Columbia University here in New York City. Most of my research has involved complex systems, that is, systems that have a very large number of strongly interacting parts, and that includes physical systems, such as the motions of stars and gas in galaxies, biological systems, such as how genes regulate the expression of other genes, social systems, such as the emotional interactions between therapists and their clients in psychotherapy. And lately I've been doing more data science things, in particular machine learning and AI to measure peace from news and social media in different countries. So this will be machine learning on quantum computers. So I'll first provide a good introduction to machine learning. Then I'll describe what are classical neural networks. And every time in this talk, when I use the word classical, usually in blue, I'll mean non-quantum. Then I'll show how we can train these classical neural networks, and then show how we can train quantum computers of 4 different types. First of all, quantum computers that use quantum Dirac type operator gates. Then hybrid computers that are partly classical and partly quantum. And then quantum Hopfield networks, and then quantum annealers. So the established paradigm is that if we have a problem to solve, we have data and a method to solve it. From that method, we form the equations that represent it and then translate that into computer code. We then give the program new data and run the computer program, and the computer program gives us the answer. This new machine learning AI paradigm is different. We do not program the method to solve the problem. Instead, we program a system that learns to solve the problem, and then that system uses the new data we give it to solve the problem. So we train this machine learning system on samples we already know. We then give it new data, and the machine learning system gives us the answer. Now, this can fail if the machine learning system is not smart enough to learn how to solve the problem, or we don't give it enough correct examples for it to learn how to solve the problem. Now, I'm a physicist. Are you telling me that I don't write down the equations based on physical law to solve the problem? How do I know the explanation? My equations are the explanation. Yes, I am telling you exactly that. Machine learning and AI is a different paradigm. You train a system to learn, and then that system tells you the answer. Look, in physics, we've gone first from qualitative descriptions to analytic equations, which often were too complicated for us to solve them, especially because of nonlinearities. And so we threw away the nonlinearities to solve them, which were sometimes the most important parts of the equations. Or we finite difference those equations so we could do numerical solutions on computers. But often those solutions do not do well across problems, for example, like in predicting the weather or in predicting climate, that scale over a large range in space and time. Now, the machine learning AI system is the explanation. So we know how we've created this system, the equations that went into programming it. We know the data we use to train it, but we can't fully explain how it works. But even not fully understanding how it works, we can use it to do a lot of really good and important things. But I know this business of not understanding how it works really upsets some people. So I want to make it clear that we've been here in physics before. So when Isaac Newton wrote his book, which is called the mathematical principles of natural philosophy, that is, of physics. In that book, he writes down an equation for the law of gravity, that the force of gravity is proportional to the product of two masses divided by the square of the distance between them. When Newton's book comes out, this is heavily criticized because people ask, well, how does it work? How does this mass feel the other mass? That all we have is this equation. This is a return to medieval mysticism, some of them said. And this criticism is so hostile that a few years later, in a second edition of this book, Newton adds a section where he addresses these criticisms. And he adds this line. The whole book is written in Latin. And he adds this line, which has become one of the most famous lines in the entirety of Newton's book. And what it means is, Newton says, I do not make any hypothesis as about how this works. What's important is I have this equation. And with this equation, I can predict, and it turns out accurately, that the diameter of the Earth from the North Pole to the South Pole is a little bit shorter than any of the diameters of the Earth along its equator. The Earth is a little fatter along the equator. And it makes sense for the first time, this equation, of why there are tides in the ocean and why we have high tide twice a day. And this equation can predict with the greatest accuracy the motions of the planets across the sky as they change during the year. And this is exactly the situation we find ourselves with machine learning and AI. We can't really explain all the pieces of how it works, but it can be tremendously useful. Now, if you think about it a little bit, in fact, these analytic equations that we often couldn't solve, or the numerical solutions that don't scale very well with problems, also have limitations. But we're so used to using them that it makes it a little bit harder to see those limitations. So this is a classical neural network. It's designed a little bit like the visual cortex in the brain. So if I turn around here, you can see from the top back of my head, underneath this is where my visual cortex is. And there are nerve cells there, and there are connections between the nerve cells, which are called synapses. In the neural network, we're going to call them links. And there are many layers in the visual cortex, and this is a feed-forward network, so it computes from the input to the output. So here we have a number of inputs, the links. It goes to a number of intermediate layers, which are called hidden layers, and then it goes to some output layers. And this is how it works. We have a node, I, and it has a certain value, x sub I. And the output from that node will go into other nodes. It depends on the value in that node times a parameter called a weight factor. And these are called weights in most neural networks. In the large language models, these are usually referred to as parameters. The input into that node, J, is a function of the sum of the inputs multiplied by those weights. And this function is typically a nonlinear function, and there are several different versions that you can use for that. And there's usually many layers from the input nodes to the output nodes. So how do we train a traditional network like this? Well, what we're going to do, we're going to give it examples of known inputs matched with known outputs. What we want is for the system to give us the correct output for each known input. But we want something more. We want it to generalize so it gives us good outputs to inputs it's never seen before. And the algorithm to do this is called back propagation. The way this works, we're going to give it a fixed input, and we want it to produce a certain output. So we're first going to do a forward pass. We're going to compute from the input over here to the output over there. And it's not going to match what we want, so we're going to define a cost function, which is the difference between the output we got and the output we want. And next, we're going to do a backward pass. We're going to work our way backwards through the network to keep changing the weights needed so the output will be closer to the output we want. And this is called, as I said, backpropagation. It's really an optimization problem. We want to determine the weights. And there are additional parameters, also called biases, for each neural network, so that it minimizes the cost function. Again, we're going to do a forward pass from the input to the output, find the cost function, and now we're going to do the backward pass. And the brilliance of the backpropagation method is what we're going to do is use the chain rule from calculus to go layer by layer backwards through the system, and at each point compute the partial derivatives of each parameter and how they depend on the weights and the cost function. Once we have that, now we know how everything changes. Now we can do a numerical gradient descent method to find the place where the cost function is minimized as a function of the weights. And there are a number of different ways to do this. We can do this gradient descent on all of the training data together, or we could do what's called stochastic gradient descent, where we pick at random subsets of the training data to do it. So why does this converge? About 10 years ago, some of the people who are the top people today in artificial intelligence asked this question and proposed some answers to it. And in most optimization problems, what you see is, usually you see like a two-dimensional surface in a three-dimensional space drawn, or you see a single two-dimensional plot with a lot of contour spaces. And people are always really worried that, they're going to wind up in the wrong local minima, and then they're going to get the wrong answer. In fact, what these people showed 10 years ago, that's not the right way to look at this problem. What's going on here is we're dealing with a very high dimensional space, like hundreds of thousands of dimensions, or in some of the large language models, literally hundreds of billions of dimensions. And the critical points in this space don't look anything like those two or three-dimensional plots. Those critical points are mostly saddle surfaces. That is, you get attracted into that critical point in one direction and pushed out at another point. And what actually happens during backpropagation, the reason why you don't get trapped in the bad local minimum, is you're bouncing around in this very high dimensional space until you wind up in a local minimum that's good enough to match the cost function. And it may not even be unique. So here's an application of this. This is using the MNIST data sets. This is 70,000 handwritten digits written by workers who worked in the 1990 census and high school students in Bethesda, Maryland. And each digit is 28 by 28 pixels, each pixel with a grayscale from 0 to 255. And this is some examples of what those digits look like. This is obviously an 8. And the neural network now, we're going to have a two-dimensional array of 28 by 28 pixels. So the first thing we're going to do is flatten it to a 1D array of 28 times 28, which is 784. So we have 784 inputs here. Now, what's not usually explained when people are explaining what's being done here is what we're doing is we're basically taking 28 horizontal slices through each image and pasting them end to end. This neural network never sees anything that looks like that 8. So it's doing something very different than what we do when we identify this as an 8. And even though it's got all the disconnected pieces of the 8, somehow the neural network is able to put together a way of seeing how there's a pattern in that allows it to identify it as an 8. And in this case, this network will have 128 hidden layers. So it's 128 nodes in the hidden layer, one hidden layer, and it will have 10 output nodes, each one representing a digit from 0 to 9. And the algorithm to solve this, as I said, to train this is backpropagation. And the usual textbook example, you give it 60,000 images and you test it on another 10,000. And this is the results of this neural network, which means it gets 97% accuracy, identifying this is an 8 and that is a 6. Well, as time went on, people found much better networks than having things densely connected. Jan LeCun and his collaborators developed what became called convolutional neural networks. So what you do here, you have pieces of an image that all go to the same place, and that gets pooled together. And you alternate layers of convolutions and pooling and convolutions and pooling, sometimes 100 or 200 such layers. In fact, this is pretty much what happens in the visual cortex. There are about 6 major layers back here in the visual cortex, and things are not densely connected. There won't be enough room for all those connections in the brain, so this is much more like the structure of the brain. But one of the points here is that when we run into trouble doing things, since a lot of things are based on biology or psychology, we should go to the biology that they're based on and see if that gives us different ideas on how to do things. But this neural network is not like the visual cortex in a lot of other ways. The brain does not have activation functions like the ones I showed you earlier. The brain is at the synapses. There are discrete and dynamic chemical interactions between lots of molecules going on and fights between activators, inhibitors, a lot of other things going on. Jan LeCun, who developed these convolutional neural networks, has said that, if you're trying to figure out how to make a mechanical machine to fly, and you're doing it by looking at birds, what you don't want to do is take the bird too literally. You don't want to build a big metal machine that's going to flap its wings. What you need to understand from the bird are the principles of aerodynamics. And if you understand those, then you understand that for something to people to fly in, it's going to be much better to make it out of metal and have fixed wings. So people continue to add more of these layers together, and a few years ago developed the transformer in a famous article published by Google entitled "Attention is All You Need." And this consists of very similar, although not exactly the same types of layers as in the convolutional network. There's basically a layer that identifies which pieces of that layer are most important, and then a layer that acts like that max pooling layer. And you have a whole bunch of these layers together in the first part, which is called an encoder. And when the input goes into that encoder, it makes a representation of the input. And then you can put that representation into the decoder, and then that can transform that representation to make the output. So, for example, you put text in English into the encoder. It encodes it in some way that has some of the meaning of the text, and then the decoder can output that text in French. And these are the basis of the large language models. So the large language models are basically the decoder part of the transformer. And we start by typing something in, a text, and that text is converted to vectors. That is, the text, the elements of the text, the values of those elements somehow contain information about the text. And what happens next is it's going to go through a series of layers similar to the transformer and convolutional neural networks that first link together and see what's most important, self-attention layer, and then we'll forward process those. So here we have, it will first look at the prompt and connect it, see which vectors it already knows that are similar to it, and it works through these stacks of processes until it drops out the next token. And a token could be a whole word or a part of a word, and it goes one token at a time. Well, how do you train this system? It's not just back propagation. First of all, there's a pre-training. You try to predict what's a missing piece. You take something away, and you can see how you need to adjust the weights so it correctly guesses the missing pieces. Then you give it samples of inputs and outputs, especially those specific to the domain or area you're trying to use the network for. You can do reinforcement learning. This is how DeepSeek was done, where you give it different rewards for getting the correct answer. And you require it to go back to see what steps it could have done better, and it can do that all by itself. Maybe you do reinforcement learning with human feedback, which means you have the humans overseeing it and helping it when it gets something really wrong. Maybe you do it using what's called a generative adversarial networks. You have two neural networks, each trying to get the same answer and each trying to challenge themselves. And you can also add additional components now called experts or agents that are doing more isolated tasks within this structure. So this whole process of training this system is a much more artisanal craftsmanship process because, you keep trying everything you can think of. Some of these things are synergistic. Some of these things are opposite to each other, and you keep doing it. This is much more like how people used to build medieval cathedrals. You build the cathedral, and if the wall is bending out, you put a flying buttress to hold it in. And then you come back 10 years later, and you see that at the top of the flying buttress, there are cracks, because stone is very good in compression and not good in tension. So what you do, there must be tension going on in the flying buttress, put a little more weight at the top. This is a very different approach to the world than what we're used to doing in physics, where we have much more mathematical and formal methods. So why am I telling you all this? The lesson I want you to come away from this is that, the people who do this do a lot of different things in order to make this work. There will be no simple change to make a quantum system into a large language model or a more sophisticated AI system. Now, the classical computing is years ahead of quantum computing in developing these very powerful architectures. Transformers are almost 10 years old now. Convolutional neural networks, 35 years. Backprop, 50 years. And in quantum algorithms, where are these? Where are the large language models and the adversarial networks and mixture of experts and reasoning models and other things? And I think the reason for this, physicists are been partly siloed, although I think that's changing right now. And really, we're not aware of what's going on in computer science. So I think that's part of it. But maybe another part is quantum is harder than doing the conventional things. Quantum is very good at doing linear algebra and Hilbert spaces, but maybe it's not so good at optimization and training algorithms. So maybe it's going to be interesting to see how quantum can do this. But the point is, quantum should be better at machine learning and AI than classical systems. In quantum, we have superposition, which is more efficient. Each operation works on all the states of one qubit at once, or all the combinations of states of a set of qubits at once. And we have entanglement. Each operation can work on many different things that are even far apart from each other. And maybe, most importantly, the quantum is a high-dimensional system, which is maybe what we need to solve more complex problems. That in a classical system, if we have n bits, the dimensionality of the system is 2 times n, but the dimensionality of n qubits is 2 raised to the n. So maybe we need new architectures and new algorithms that use these quantum features to do more powerful AI. Okay, so now let's get to training quantum computers. So I said I'm going to talk about 4 different types of quantum computers. Quantum computers that use full Dirac gates, like using these matrices. So the program uses only those gates to solve the problem. Next, hybrid computers that are partly quantum and partly classical. This is sometimes called variational quantum circuits, which will have mixtures of hybrid and classical components, of quantum and classical components. Here we're going to use the non-quantum parts to find the parameters for the quantum parts that solve the problem. Now we're going to talk about quantum Hopfield computers. Here we're going to here each qubit is connected to all the other qubits. We're going to use some nodes as input and others as output, and each node will be connected to all the others. Then we're going to use a new paradigm, equilibrium propagation, to nudge the output to the output we want. And we're also going to look at quantum annealers. In this case, we're going to turn things around and we're going to train the problem and not the computer. So this is training a quantum gate computer. Okay, so here we're going to have a computer that has full Dirac gates. We're going to use only quantum gates like these rotation matrices, Hammond operators, conditional knots, a whole bunch of other things. And there's an HHL algorithm that is pretty good and powerful at solving some linear algebra problems. For example, eigenvalue problems like this. But it turns out this method has very severe limitations. The matrices, the dimensionality of the system needs to be sparse. There are bottlenecks in preparing the input data. And I couldn't find one example of using these Dirac gates alone to solve the MNIST data set. Maybe someone has published that. I haven't seen it. But nonetheless, although this can't do it alone, this is a good component to put in a quantum classical hybrid system. So again, the lesson from this is quantum computers using only direct quantum operator gates have limited ability to do machine learning. Okay. So now let's get up to training a hybrid quantum classical computer. Again, these are called variational quantum circuits. The classical part of the machine will do the learning, the maximization process using the quantum operators. So the concept is we're going to train the system with known input-output pairs, like any other sort of machine learning. We're going to use classical computing to encode the classical data into qubit values. And then the quantum computing will compute a quantum circuit as a function of a classical parameter and get the output. Because the quantum is best at doing linear algebra, this is going to be a very fast step. And then we're going to use classical computing to find the value of that classical parameter that minimizes the cost function, because classical is best at doing the optimizations. So again, what this looks like, we're going to have a classical pre-processing where we're going to convert the data into qubit values. We'll put that into the quantum system, and we'll see what output we get for a specific value of one of the classical parameters. And then we're going to do that a number of times so we can predict what parameter we should put into the quantum system in order to minimize the cost function. So in terms of the pre-processing, we want to encode the classical data to the quantum qubit values. And we have a number of choices here. We can use the different quantum phases. We can use multiple qubits. We have a lot of different ways to represent the data we're putting in. And even more complex ways, which in the machine learning jargon are usually called kernels when you're using nonlinear transformation of the input. So remember, we're starting off with a 2 times n classical space, which we're mapping to the 2 raised to the n quantum space. So we have a lot of flexibility on how we do that mapping. So now in terms of the parameterized quantum circuit. So again, this circuit usually consists of non-parametrized gates, like a conditional NOT gate, because we need that to do the entanglement, and maybe a series of parametrized gates. Here are these rotations, each of which depend on an angle. This system now is usually referred to as a noisy intermediate scale quantum system, because the decoherence of the hardware means the quantumness slowly leaks out, and errors increase with the circuit depth. So what we're going to try to do is to minimize the depths of the circuits and maybe use error correcting codes. But we're going to make good use of the current hardware by minimizing the number of gates, minimizing the circuit depth, and minimizing the number of connections between things. Now note, there's no back propagation here that's possible, because that would require knowing all the values in the steps in the quantum computation. And we can't do that, because as soon as we measure them, we collapse the wave function, and so we lose what's happening. So we can only measure this at the end of the calculation, and that's why we're running multiple passes through this as a function, different functions of the parameters, and then using the classical part to help figure out what's going to be the best value of those parameters to minimize the cost function. So there are lots of different quantum components we can put in the parameterized quantum circuit. I'm not going to go through any, or actually even all of these. They're all in the reference I've given at the bottom here. And if you want to try this yourself without a quantum computer, both Qiskit and Penny Lane and Yao from Quantum BFS all have quantum simulators, so you can program this sort of stuff even without a quantum computer. We've been using Qiskit and Penny Lane. So now we have this training set where we have some known input and output pairs, and we're going to try to minimize the cost between the output we're getting and the output we want. And this is just like the second part of back propagation, where we use gradient descent or stochastic gradient descent. But the reason why there's no propagation here, back prop here, is we don't have those partial derivatives that we get from the chain rule for a classical computer, and the machine learning has to estimate them without the knowledge of being able to do the calculus. So that's why we have that loop, and that's why we're running multiple estimates. And this is an example of that. This is from an online class from MIT. We're back to the MNIST data set. And here they have a classical layer going into the computer. For the classical layers, they're using PyTorch. And for the quantum layers, they're using Qiskit. And then they have a very simple quantum circuit and then a classical output circuit. So they have one classical input layer. They actually, although it's not shown here, have two classical convolutional and max pooling layer pairs. They have one fully connected output into the quantum layer and then another fully connected classical output. Here they actually trained on 200 images, tested 100. They're actually getting 100% accuracy. This is not as phenomenal as it looks. You do not need to train this system on 60,000 images. People have shown that either 50 or certainly 100 or definitely 200 images are actually good enough to get pretty good training on classical convolutional neural networks or fully connected neural networks. And this is a more sophisticated approach. Here, they're trying to understand all the different engineering steps, manufacturing steps that go into creating this integrated circuit on the chip, and they've done this with a hybrid quantum classical system, and their conclusion is this hybrid system consistently outperformed the classical baselines across multiple evaluation metrics, demonstrating robust predictive capability in this small data regime. So it worked well for them for this problem. Now we'll get to a third type of quantum system. This is a quantum Hopfield system. So we're going to have a Hopfield Ising network. That is, each qubit is connected to all the other qubits. This is going to be a pure quantum system. There are going to be no direct operator gates here. Now, I know there are some people who think, there may be even some people in this audience that think, why are we doing this? This is not a real quantum computer. Notice I put the word real in Comic Sans here. And quantum computers must have gates. Why are we doing this? So the short answer here is that it works and that this approach can solve practical problems. The longer answer here is that it's using the quantum energy functions between the nodes of the network, and we're looking for the energy minima, the ground state, which is the heart of doing any quantum problem. And we're going to have some of the nodes as quantum input nodes and some as quantum output. The algorithm is going to be similar to what we saw in the classical case, although it's going to be a different algorithm, where we're going to try to make the output approach the output we want from a training set of input-output pairs. And this algorithm is called equilibrium propagation. And it's a quantum avatar of the classical back propagation. And basically, this is going to do the quantum optimization that the quantum gates alone cannot do. So this is what the quantum Hopfield network looks like. Everything is connected to everything else. We're going to define some things as input and some nodes as output. And the nodes will have discrete values. These are quantum nodes. And again, each node will link to all the other nodes, but with a very, very special weight function. That is, the weight functions are symmetric. Now, you never see this in any of the classical neural networks. The reason why Hopfield has done this is that if you do this, you can actually produce an energy function that has real physical meaning, which you cannot do for the conventional neural networks. You can make believe there's an energy function there, but this is a real energy function with a lot of physical properties. And we can take up the total sum of the energy as the weights multiplied by the energy difference between any two nodes. There are no layers here. Everything works together. And as I already said, we're going to pick some nodes as input and other nodes as output. So how does this work? We're going to fix the values of the input nodes. We're going to find the energy minimum, and then we're going to ultimately read the values of the output nodes. And we're going to have an energy function of how the nodes interact with each other. Well, why are we using this architecture at all? It turns out that many hard problems can be transformed exactly into this architecture. That is, there's a way of estimating the complexity class of algorithms. That is, easy problems where the computational time or computer memory needed depends on some factor that scales as a polynomial. So those are called polynomial problems. But there are much harder problems where computer time and memory scale as exponentially or faster than exponentially, and so those are called non-polynomial problems. And it turns out a very broad class of non-polynomial problems can be reconfigured as exactly this quantum Ising network. So first of all, this is a publication that goes through the Ising formulation of all these problems. So let's try to make some sense of this, of what these problems have in common. It's kind of hard to do, but if you think about it, this traveling salesman problem, where we have a bunch of nodes and you want to find the minimum distance between all the nodes, visiting maybe each node once and things like that. And what happens is the local interactions, when you change one link, it changes the whole problem. what many of these non-polynomial problems have together in common is this property that something that happens at the small scale instantly bubbles up to the larger scale and affects everything else. And we can't do slices through this and do subpieces separately. Well, this is just what happens in real life. So here RL stands for real life and not reinforcement learning. So in industrial processes, we have processes that are very slow and very fast. In maximizing supply chains, we have similar things. In economics, we have the connections between micro and macroeconomics. In social systems, we have the connections between people and society. And that's exactly the sort of things we have in this Hopfield Ising quantum annealers as well. Okay, so let's compare the classical computer network to this quantum Hopfield network. Well, in the classical neural network, typically the nodes have continuous values. In the quantum network, they have discrete values. They don't have to be zeros or ones. One of the cases I was looking at and using was a Q equal 4 Potts model. So that has a total of 4 energy levels. And you could represent, or 4 levels, you could represent them either as integers or as angles in how the nodes interact with each other. The connections between the nodes in the classical network are algebraic activation functions. In the quantum, they're going to be the quantum rules, again, with the caveat that the weight functions are symmetric. The topology of the classical network is feed forward. We compute from the input to the output. In the quantum Hopfield network, it is fully connected. Each node is connected to all the others. We compute everything, everywhere, all at once. And we do the training forward pass in the neural network. We compute from input, output. The analogy of that in the Hopfield network is we find the free state energy minima, where we're not trying to do anything yet. The backward pass in the neural network is done by backpropagation, where in order to get the output we want, we know how to change the weights. We can't do that in the quantum Hopfield network. We can't just fix the output nodes because that changes everything and what's happening in the inside. So backpropagation won't work. We need to do something different. And that something different is the equilibrium propagation. So just like all the other cases, we're going to give this examples. We're going to put known inputs into it, and then we're going to get known outputs is what we want. And as usual, we want to get the correct output for each known input, and we want the system to generalize to have good outputs to inputs it's never seen before. And we're going to do this through equilibrium propagation. So what we're going to do first is fix the input. Then we're going to do a forward pass, and we're going to get the free state energy minimum. Next, we're going to weakly hold the output near the output we want. So we're going to use this nudge, which acts like an external force, that's going to propagate inward and create a new external state. So the backward pass will be how the outputs will change when we let them propagate back. Now, it's surprising, to me at least, that when we do this and do this in a succession of states, that's why this is called equilibrium propagation. We're going through a set of equilibrium states, that this actually works so we can actually understand how to change the weights so that we can get the outputs we really want. This works because it's derived. Now, I'm not going to go through the derivation of what the equation looks like. That's in the Cellier-Bengio paper, which is shown here. But basically, it works because we can define 2 energy functions. The fact that the weights are symmetric allows us to do an internal energy function. We know the force we're putting on the output nodes, and we can integrate that to get an energy function that gives us the internal energy external energy function. And knowing these two together, after we give it the nudge, we know how we should recalculate the weights. And we keep doing this slowly because we want to do it in an equilibrium way. And here's an example of that doing the MNIST data set. This is our usual 8. This was done on the D-Wave Systems DW2000. This is the reference in Nature over here. This machine has 5,000 qubits, which are binary 0 and 1. The network that they're using to do this is logically fully connected, but the machine itself isn't. It's divided into 4x4 squares, which are connected to each other. So you have to do a lot of other stuff here to make this work. The weights are between 4 and 6 bits each. 4 qubits each are used to define the digits 0 through 9, and they used equilibrium propagation, trained it on 1,000 digits and tested on 100. And when they do that, they get 89% accuracy on the 1,000 test digits. Now, if they had more qubits and more time, they can actually run a simulation of what would happen in that case, and that would get them even closer to 100% accuracy. So another approach, we had here a few meetings ago of this meetup where we had a really nice talk from the people at Quantum Computing Inc. who showed off their Dirac 3 machine. And in this approach, you're trying to find the ground state of a network of qubits. And this is also going to be pure quantum with no gates. So in this case, we don't train the quantum network. What we do is we train the problem. That is, we transfer the problem into this form where the energy depends on a variable to first order, variables multiplied together to second order and third order and fourth order and fifth order. So we're building up complexity of the problem. And those are going to be the variables. And what we're trying to find, which we will find when we get to the energy minima, these coefficients at the beginning here. And those coefficients then tell us what the answer is to the problem. And they showed very nice versions of this solving some very nice standard machine learning problems like XGBoost and decision trees and logistic regression. So if you can't train the machine, train the problem. So in summary, training a classical or a quantum computer from a set of known input-output pairs is an optimization problem. On a classical computer, this is done with backpropagation. But backpropagation does not work for a quantum computer. As far as I know, there is no quantum gate-only machine learning training algorithm and no piece of hardware that's been able to do that. So therefore, there are 3 approaches to training quantum computers. We can do a hybrid classical and quantum computer using variational quantum circuits. Now, the classical component helps do the optimization needed for the training. A Hopfield quantum computer, where we have equilibrium propagation, training the system by slow nudges in the output nodes that propagate in the correct way through the whole network. Or analog quantum annealers, which transform the problem rather than teaching the computer how to learn, that can find the coefficients of the ground state. So I'm going to end with a shameless ad from my YouTube channel, which is Larry PhD. It turns out there are a lot of Larrys with PhDs on YouTube. So I have the direct link here. If you have troubles finding my YouTube channel, if you just type in quantum computers in 20 minutes, that's one of the videos on that channel, and it will take you to the right place. Thank you.